let's do 7. We already have that. No, let's take that. Yes. All right. Oh, yes. There we go. Yep. Test. See, the Hangout is working. Test. Sorry? Yeah. Only for the suckers that don't take this course. Let's do this. Yeah, I have to think about the chemical biophysics Python visualization thing as well. This will be on the May 13th, but they've asked if we're still interested for it. They put in, yeah, they have a 3-hour slot from 10 to 1. That's a good question. Okay. Okay. Mm-hmm. Is that with Matplotlib? 3D plotting? Oh, you can do it, yeah. Yeah, 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 yeah. Mm-hmm. Yeah. Yeah, it's just it. Yeah. I think that would be nice to add. I find 3D plotting a little bit cumbersome with that. I don't know if that's better, but I don't know if there's anything they can do, like molecular visualizations in fact. We can find something like that. So we're still doing it, right? Okay. Right. Okay. 3 hours. Yeah. Yeah. Okay. Good. Yeah. Right. Yeah. Right. It's biochemistry. It's biology, chemistry, and physics. CBP, chemical biophysics, and it's basically grad students from all those fields. Oh, okay. Oh, for all those waveform files? No, they can just be in the same directory.
It's going to create separate.
Oh, that's
I
fine.
was going to include them. I assume you have.
You can.
It's easier if I do that.
Well, these are a little big, so up to you, but
set it up to same.
Yeah, definitely don't upload them one by one back to the. Yeah, no, it might be easier to have it in a directory then. Sure, but Just make a note somewhere. Okay, the files are supposed to be there and there. So when I try to rerun your stuff, I know, okay, I have to make sure those files are there.
Or change.
Yeah. Well, rather not. Well, I can, but it's, you know, I want to see your code do the thing that it did for you, right?
You want the pure experience.
Yes. So,
I don't think FI
Yes.
mhm. Not our array itself. So you can't get the array of all reals, but you can get, for each number, you can do real. So that's just part of the complex class. Sorry, but what is she trying to do? Sorry, it's not very
So
much.
this is how I
Oh, yeah.
I want to see
Why you want?
no, because when you calculate the powers, she's actually no part as
Yeah, of the transform, right? But before you transform, you have to work with it as a complex number. It's the Fourier transform that you have to take the square of the imaginary and the complex part. So here is this is still the Fourier this is still the original one.
So
right?
actually,
Or not? So okay. Oh, I see. Yeah. So that is already the trans. So perspective. Yes. Okay, I see. So yeah, no, you can. So you don't. Right. But you don't have to make them as arrays, right? You don't need an array of the real parts and an array of the imaginary parts. The complex array has real and imaginary parts in it already. So you can just go over the complex array and compute. Right. So your f, go over that, and for each element compute the sum of the squares. Right.
So right.
No. So what you have to do.
Yeah.
So first of all, you don't use parentheses. You have to use square brackets, right? Square braces for excess elements. So this is Fortran. Want to do it as it's in C++. So these are square brackets. That's the wrong notation. That's the notation, right? If you remember. For arrays, it's always square brackets. Okay. Yeah. And then since this is a complex number, you can do imag of that as a function, basically.
So there's also for array.
Yeah, because the array so as soon as you say fi, that's now a complex number, and everything that works for a complex number will work. But
So actually, I can.
yeah, that's right. And then the same with the imag. Yeah. So it doesn't matter how, but that will work absolutely. Yeah.
I guess
Hey.
The question about the
Okay.
when we are calculating the power spectrum, do we create a function that do the component-wise magnetic square, or you have a library for that?
Yeah, no, I think there's a library for that. So that's something you have to write yourself.
To do it by hand.
Yeah,
Sure.
yeah.
And finally, we have to decide which one is the which five candidates
are the best. Yes, that's right.
Yeah, way detection. So do we do that also by eye, or we have to do some sorting algorithm, something like that.
You can sort. It's not a big. You can do that. There are standard sorts there, or if you want, you can script it in Bash. I don't really care how you sort it. But yeah, so
that's not a mandatory for this.
No. Like this with 30. If you sort it by eye, okay. There's not, I mean, it'll be way more elegant if you just have it sorted, right? So that'd be much better. But don't like if that takes you a day to get working, don't do it.
And one more thing is that when we're calculating in the product, we use d dot or something else.
Yeah, something like d dot.
Right?
Yeah.
Because there's a question mark in the manual.
Well, the question mark, it's sort of a generic notation because there's something there, right?
Okay, yeah.
It's d dot or s dot or z dot. That's right. Yes. Yeah. All right, we're going to get started. Before we do that, any questions about the homework? I answered a few already, but okay. My mouse here. So today we're going to talk about ordinary differential equations and how to solve them numerically, and with applications to molecular dynamics and n-body simulations. So first we'll do sort of a bit of generality on ordinary differential equations, which is a numerical topic on its own, like how you solve them. And then, as it turns out, many of the important cases that we deal with in physics and astrophysics, as well as in biophysics, deviate from that enough that we actually don't use some of the standard things that you might use in differential equations. And so we look at them specifically. And I picked out molecular dynamics, so simulating classical motion of atoms and molecules, and n-body gravitation. First, to set the stage, ordinary differential equations, different from partial differential equations, is that they have only a derivative with respect to one variable, often time. So the x dt is some function of x and possibly of t. It doesn't have to be of t, but it could be. And you could have sets of those equations. dx1 is some function, dx2 dt is another function. So you could have a set of those, but it's still ordinary as there's only a different derivative with respect to t. You can have higher order derivatives as well. Second order derivatives are very common, especially in Newtonian dynamics. So, because the second derivative of position would be acceleration of force. So that doesn't really matter that it is second order, because we can rewrite this by setting the first derivative to be a new variable x2, and then that just rewrites the whole thing into a first order differential equation, but now a set of them. So as long as we look at a set of first order differential equations, that's the general case that we have to solve, and any other ordinary differential equations can be expressed in terms of that. So that's what we'll do for the next little while, just sets of first-order differential equations. Only one derivative. And so this does include Newtonian dynamics, and therefore has a wide range of applications in physics and astronomy, as well as, to some extent, biophysics. Here's some examples, just to show how widely they can occur. Some ecological models, predator-prey models, X could be predators and Y could be prey, can be casts in an ODE. The harmonic oscillator, which as physicists we all love and adore, and everything should be a harmonic oscillator. The rate equations in chemistry, so you could have X, Y, and Z here be species or concentrations of species, and they would react and change their concentrations according to some ODE. We could have very simplified weather models like the Lorentz system, which isn't good for predicting the weather, but is very good for showing that weather predictions are very hard because it's a quintessential chaotic system, showing that there's limits to how far you compute the weather. In any case, they occur in all kinds of scenarios, and so we want to know how to solve them. Usually you can't solve them exactly. That's the point, obviously, of this course. And so if we had this set of xi variables whose time derivative is given by some function, what we'll do, since it's going to be numerical, is we won't be able to solve this for every t, because that's infinitely many t's, and although the computers are powerful, they can't deal with infinity very well. So we're going to evaluate f at some discrete points, and we want to get the xi's at discrete points. We'll do only, in this case, initial conditions. So we'll start xi off at some time t0, and we'll see how it evolves. You could have different cases where you basically specify the endpoints. In that case, it doesn't become much different from what you would typically do with PDEs, and so we won't consider that here. And then there's different ways you can go about. You could say, well, I just want to have my function at specific times, so I'm going to take time steps. And as it will turn out, if I take those time steps too large, things become unstable. So we started with the PDE a little bit as well. So you'll want a small enough time step so things are accurate and stable. And then we'll get, by some sort of numerical scheme, the xj at t. And then, much as in the PDEs, we could have this be sort of implicitly or explicitly. We'll see that soon. Okay, so we'll discretize time. We'll discretize and basically the whole idea is that evaluating f, you want to minimize that. Think of f as a very expensive function. The more times you have to evaluate f to get an accurate solution, the longer your PhD takes. Okay, so I just want to warn you against something called stiff ODEs, although I won't get into it too much. Stiff ODEs are ODEs that are hard to solve. That is actually pretty much the technical definition. It doesn't go much beyond that. But they are difficult to solve typically because it's really hard to find a time step that is small enough to both resolve this sort of the fast motion within your system and big enough to have this thing solve your problem in reasonable time. So usually wide variations of time scales or other scales. It's similar to the idea of a condition number in PDEs, where it might be hard to invert a matrix because the scales are such. So now, when you have such a case, there are sometimes methods that work better for stiff ODEs. They can be sort of doing a very careful adaptive step size, where when you hit these fast instability, these fast modes, you go with shorter time steps, etc. So not all methods are equally suited for stiff ODEs, but this is all I'm going to say about it here, just because it's worth knowing that you might hit upon one of those, and then you basically look into whether your numerical method says it's any good for stiff methods or stiff ODEs or not. Okay, so let's be a bit more specific. How would we solve this? Let's do it sort of naively and see where this leads us. So we're going to just do a Taylor expansion. We'll say, okay, we have dx dt. I want to take a time step h. H is the historical notation for time step, not my choice. H. And so if the derivative of dx dt is f, then x at the next time step, so time h later, is xn plus that time step times the derivative to first order in a Taylor expansion. So that's a simple way to go from a point xn, evaluate the function once and get xn plus 1, or xn x at one time step h further. And this is called forward Euler. And so here's sort of the formal way of showing that. But you can see that we make a little error here of order h squared. So if you wrote down the next Taylor expansion term, we'd find that it goes as h squared. So the smaller h would be, the smaller our error. So you would think, well, we just take h smaller and smaller, and we'll be fine. This is perfectly reasonable. But this order h squared, you must realize, is made at every time step. And so if we want to get to a specific interval, say from t1 to t2, then the number of time steps I need is t2 minus t1 over the time step size, so n. And so the number of steps I'm going to take is inversely proportional to h, which means that once I went through all the steps to get to t2, my error is actually going to be of order h. So I derive it thinking it's quadratic, but it's actually not, right? So you call it quadratic because one time step is quadratically accurate. But your global error, the error that actually matters when you're integrating, is of order h. So that's not particularly accurate. That's not the worst thing about this particular method. It's also not very stable. I'm going to show that with the harmonic oscillator, our best friend. So here it is in slightly different notation, but x1 and x2 are the components here. This is the partial. These are the two ordinary differential equations that govern this. Now, if I do this forward Euler here, because everything is linear and simple, what it boils down to is that at each step, I basically have a linear mapping from my previous point to the next point. So x1 could be the position, x2 could be the velocity or momentum, and basically this is the matrix that I have. So each time I apply this matrix. So whether or not this is stable really depends on the eigenvalues of this matrix, right? So here's what happens when I do this. So here's the matrix again, and I've started in the middle here, and I just applied this matrix again and again and plotted the result. I get this spiraling out. At first you might think, well, maybe I chose the wrong step size, right? It's now unstable. Your h should be smaller. What did you choose? It actually turns out it doesn't matter. If you compute the eigenvalues, you find that of that matrix there is 1 plus or minus IH, which means that their magnitude is the square root of 1 plus h squared, which is always bigger than 1. This means that no matter what h I choose, this is an unstable method. Okay. Even for something as regular as the harmonic oscillator, where there's no nonlinearities, like everything is nice and smooth, this should be simple for a numerical method to get right, and it doesn't. So this is why you don't use the simple forward Euler. Okay. So what do you do to fix that? Well, see, we're spiraling out, right? So that's because we made our approximation of saying, well, x is related to xn by taking, I'm going to go one step further back. Okay, I decided to evaluate my derivative at the time tn. I could have decided, which is equally valid up to the same order, to take the time tn plus 1. This gives me an implicit method, right? You give me xn plus 1 here, and I'd have to solve this for xn plus 1. But I could imagine doing that too. So I'm kind of going in the reverse direction. So if I did that, what do you think would happen? I'd spiral in. I'm going in the opposite direction in time. Still unstable, still no good. So going forward in time, forward Euler, spiral out, backward Euler, spiral in. Well, let's take the midpoint. And that's the idea of midpoint Euler. So I'm taking the function not at the point xn, but at the midpoint. This turns out to be enough. I could do t at the half point too, but since t doesn't occur in f in this case, it doesn't matter. It's an implicit formula, right? So I have to solve this for xn plus 1. And if f is some nonlinear function, I'll have to use one of my fantastic root finding algorithms to do this. But in this case, it's linear, right? So we actually get this. It gets a little messy, I know. It gets this relation between xn plus 1 and xn. So another matrix basically maps these two. And the eigenvalues of this matrix, although a little bit more complex looking, are actually such that their eigenvalues are both 1. So this worked, going from unstable one direction, unstable the other direction, taking the midpoint, stabilize this, and you get a nice little circle in the middle. So this is easy to show here, but it's kind of generically true. The midpoint Euler tends to be stable, but in general we'd have to solve it for xn plus 1. So it's not as nice as just stepping forward. So since it's not so nice, since it is implicit, people have looked at quasi-implicit methods, because what we're really doing is kind of like, even if we solve this equation for xn, we kind of make a guess, right? Much as in root searches, and we improve that guess and until we converge to the root of the search. Why don't we sort of bake that into the solver? So there's a whole family of so-called predictor-corrector algorithms that kind of do that. So they compute a new point, that is your trial, and then they correct. It's kind of root finding built into your algorithm for solving the ODE. And one of the more common ones is called Runge-Kutta. It's fourth order accurate. So I think that should mean that the global error is third order. And what it does is it computes sort of a first guess. It's called this K1. Then it uses that guess to come up with the next point in the middle and computes a second guess of what I should add, and then uses that again for the next one and once more. And then it does some weighted average of those guesses such that everything cancels out. And so the magic, of course, is in all the details and making sure this works out to fourth order. But because we're using intermediate points, this tends to be very stable. Now, it did cost us 4 evaluations of f. Okay, so this isn't particularly cheap, but finding those roots would have cost us many iterations of evaluating f as well. So this tends to be a little bit faster, and this is actually the workhorse of a lot of just out-of-the-box ODE solver. You have an ODE solver, it probably has a Runge-Kutta at the back. It might do adaptive time steps where it tries to do something for stiff equations, and that's generally the right approach anyway. So if you're using an out-of-the-box ODE solver, what you're going to specify is not the time step. You might think so because we've had it in the slide, but you're going to say what accuracy you want of your solution. And what the method will do is it will keep decreasing h until your next point is that accurate. So you have sort of a controlled way of adapting h. Now, this can get messy, and coding this in yourself is rather tedious, so you don't, right? So the theme of this part of the course is don't code, use libraries. So GSL has some of these. Boost itself has an ODE integrator. Either one are very usable and sort of relieve you of the burden of having to debug an adaptive time step. Clear? So that's the general description. You have an ODE. You find a library. You plug it in. But that is after you've formulated your problem as a first order set of ordinary differential equations. So that is great. That is fantastic, and nonetheless, large research groups don't touch things like Runge-Kutta because it just doesn't work as well for them as they would like to. And one of those groups are the ones doing molecular dynamics. So molecular dynamics is sort of by definition, anytime you describe matter on a semi-atomic or semi-molecular scale or mesoscale, as if they are classically behaving particles. So you take n particles, atoms, molecules, stars, black holes, and they will be subject to n equations of the form m r dot dot equals the force. Maybe there's magnetic field, so then it depends on the velocities as well. That's fine. Maybe it depends on time. There's an external varying field, and some initial conditions. So this could be almost anything, but it does restrict itself in sort of the basic form to classical mechanics. All right, there's quantum extensions, but we will not go into those. And so because those particles can be anything, you can go from chemical physics to biomolecules to material science to astrophysics. I don't know why I didn't put astrophysics in here. So what does that? Why is this so different from regular ordinary differential equations? Because it is an ordinary differential equation. I can take the second order derivative and turn it into two first order derivatives and just give it to my Runge-Kutta, right? And so two things are different from it. One, this tends to be what's called Hamiltonian dynamics, and since most of you are physicists, kind of know what it is, but that implies things like energy might be conserved. There might be a well-defined equilibrium, etc. And the second thing that makes this very different from a practical point of view is that all these particles are interacting. So this force is some sort of sum of the force that each particle exerts on the other. And so the evaluation of F is not just expensive, it's very expensive. This is so you don't want to touch F any more than you really need to. So all these fancy things like Runge-Kutta or established things will evaluate F as often as they deem possible, they deem necessary to get a convergence. In these cases, you might just want to say, I'm not going for I'm going to go for a lower accuracy just to get my stuff done. And it might be good enough, and often it is, especially if you're looking after sort of equilibrium properties. It doesn't really matter as much. And so that's what makes this different. Now, it doesn't matter if these are atoms or stars. The basics are the same. Again, I'm not going to touch either quantum mechanics or relativity, so let's just keep everything nice and classical. This is just a little bit more detailed than it needs to be. The real point here is that the force that you need to compute for each particle is the sum of pair forces. Okay. So if you had a potential, it's in the Hamiltonian somewhere here, this phi is the sum over pair interactions, which means each time I compute my forces, every particle exerts a force on every other particle, and vice versa. Now, another thing that is sort of specific and worth mentioning here is this thing called boundary conditions. So for PDEs, we saw it's nice to just have, so you do a heat equation, say, well, the left side is 0 Kelvin and the right side is 300 Kelvin or whatever unrealistic case you want to simulate. For these boundary, in these cases, we're looking for n-body dynamics, and a lot of properties we might be after are actually those for the Avogadro number of atoms, so 10 to the 23rd or 6 to the 23rd. We can't simulate that. We have supercomputers, but 10 to the 23rd is just pushing it too much. So we want to sort of simulate an infinite system. You can think of it sort of, say for instance, you want to know how a biomolecule dissolves in water. So you have this biomolecule surrounded by a lot of water. But then if you just leave it like that, the water is going to go evaporate at the ends, right? So you want to somehow pretend like the water is infinite. Same for evolving the state of the whole universe, right? You'd like to do it as big as possible, but maybe it's enough just to have a small portion that is represented. How do you make something finite into something that looks infinite? Well, this is how you do it. So you take your finite volume, this red little box here, which has 6, let's call them stars in it. And I'm going to replicate this guy infinitely many times. But I'll do it such that I demand that the stars in the next box are at the exact position except shifted from the original box. Which means I only have to keep track of these 6 guys, right? I just have to make sure that I'm summing in a way that sums all the forces. Now, obviously, stuff that's very far away isn't going to influence this box too much. So hopefully there's a way to do this. But that's what you do. Now, because they're replicated, it means that if a star escapes on the right here, its counterpart here enters in the left. So part of implementing periodic boundary conditions is making sure that when they escape on the right, because you're only keeping track of the red box, you put them back on the left, and vice versa in all directions. Okay? This is a very effective way, better than just putting boundaries at the like hard walls around your universe. That's not very good or realistic. It's also not very good for like answering solvation questions. It's not good for anything. It just gives too big a finite size effect. This is the sort of the minimal thing you can do, but it causes a few artifacts. So you do want this box to be big enough. You have to make sure that your particles go back. All right. So these periodic boundary conditions are very common, even in astrophysics. Although you might argue whether or not these are real for our universe. So we call the other copies periodic images, and we'll now, I'm going to go for a little while, focus more on the molecular part of these things. So imagine that this is water, and these are water particles, or maybe even simpler, because water is a molecule. Let's take argon molecules, atoms. Just they're neutral. Like most atoms, they attract each other on long distances and repel at short distances, and they're sort of a generic potential called the Lennard-Jones potential that captures that. Okay, it has these 2 powers, one for the repulsion, 12, and one for the attraction. And in fact, this power is exactly what you get for neutral atoms. You can actually derive this one from quantum mechanics. Again, won't do that. And this one is sort of heuristic. Doesn't really matter. It kind of looks like this little one here. And the reason that this is nice is it goes to 0 very, very quickly. And so we're going to use that to make our infinite system finite. So in our infinite system, everything has to be summed with everything else. So if I have n particles, I have to have n times n minus 1 over 2 pair interactions. But if I take this potential, and rather than having the true 1 over r to the 6th here, I sort of say, well, let's just shift it up a bit and cut it off once it's pretty far away. So in dimensions units, 2.5, let's cut it up. Just say, no more potential. That's good enough. That means that I don't have to sum any of the particles that further away than 2.5 in these units, right? So as long as my box here is, say, at most 2.5, I don't have to go further than the next box. Make sense? So I just truncated it. And for this potential here, that's a fairly reasonable approximation. If I don't want to know if it's a good enough approximation, well, let's just take the cutoff twice as far and do the simulation again and see if it converged, right? Whatever quantity I was interested in, I don't know, maybe the equation of state or something, I can see whether this was good enough. And this works. This is a good way to do it. And so this turns my order n squared calculation of force to something of order n. A lot of n's, like everything in that box, but just order n. So linear versus quadratic. Great. So these are short range forces, work perfectly. A few things that if you're going to do molecular dynamics, you should know of that sort of help in arranging this sum to be finite, so that you don't actually sum over n squared and just take the zeros where they are. You can divide your system in cells, so kind of like the subdivision of the periodic cell that are of that order RC, and just take the boxes around that. That's called cell division. Or you can go a little bit more fancy, because even with cell divisions in 3 dimensions, you can imagine you have 27, well, let's say 26 neighboring boxes. A lot of them are still outside of this cutoff radius, right? So you could keep track of all the particles that are sort of close to each other particle, or each given particle, with some tolerance. And keep it neighborless and only sum over the neighbor list. And only when one of the particles moves too far, you update its neighbor list. So this way, you only sum the things that are very likely to be non-zero. And all of that can really help you not just get order n squared to order n, but reduce the prefactor of the order n. Okay? This can easily be 3 to 10 times faster doing these things than just cell divisions. Okay? So that's a good way for basically neutral atomic or molecular systems that don't have long-range interactions to become feasible. So it won't work if you have electrostatics, which is long-range, but we'll get to that in a second. Okay, so our first calculation is fine, but it's still expensive. Like, it's not cheap. We just made it sort of feasible. And so we still want a way to get away with as much inaccuracy as we can. We don't want to go run the cutoff and do something simpler. So what do we have to have of our integrator such that we can still accept it from physical principles? So these are some of the ways. We want it to be accurate to some extent that we can control. Efficient, so compute the force as little as possible. Stability is very important. We don't want our water in our simulation to start boiling just because there's a drift in the temperature, right? This should be stable. And we might want it to respect other physical laws. So many Hamiltonian systems have time reversal symmetry or conserve energy, linear momentum, angular momentum. If you're doing sort of averages in a statistical mechanics, statistical physics, you'd want phase volume to be conserved. This sort of guarantees that you have a reasonable equilibrium. All of these, or some of these, will have to be violated. They can't all be true at once you start truncating your time. Okay, these are continuous symmetries. We discretize, we break something. Okay? So you pick the ones that are most important to you. If time reversal isn't important to you, if conservation of energy isn't important, well, actually that one probably is. But linear momentum, maybe. Angular momentum, maybe not. Maybe you have water in a bucket. Doesn't have to rotate. I don't care. Right? So you choose a little bit, but these are things that you might want to demand. And so the best algorithm is the one that allows for basically the largest possible time step, given an accuracy, while maintaining stability and preserving the conservation laws that you are interested in. So this is where it differs from just ODEs, where all you really care about is, yes, few evaluations, but they're just accurate. Right? We have additional demands. So I'm going to show a few that are simpler than this Runge-Kutta, kind of look like the forward Euler, are nonetheless much better and efficient. So one of these classic integration routines is called the momentum Verlet scheme. It has many names because it is such a good algorithm, but not too complicated. It has been invented quite a few times. So I will call it Verlet scheme because Verlet did derive it. Others have too. Okay, and so we're basically going to almost do a forward Euler, but to second order. So we're going to first look at the position of one of these atoms, add its velocity times the time step, and then the force over 2m times a squared, right? We knew this in high school. And then we're going to do that, and the next thing we're going to do is update the momentum by taking not this force, but the midpoint. Now you could guess now why we're doing the midpoint, right? Doing that for stability. So if we just did Fn, we'd have forward Euler, and we know it's horrible. This wouldn't even work for the harmonic oscillator. So we're doing this midpoint, but we're only doing it in the force. Right? So it's kind of funny, and it seems to be an implicit method because we need Fn plus 1 here, right, to compute En plus 1. But if your forces are such that they do not depend on the velocity, so if you have no magnetic forces, then capital F is only going to depend on the positions, and we've just already updated the positions. So this is actually an explicit scheme when you don't have velocity-dependent forces. So you do your R, F is known from the previous positions. You plug those new positions into Fn plus 1. You compute this average and you do Pn plus 1. It's even cuter because it seems that we're computing f twice, but we don't. Because the next step around, this fn plus 1, this serves as our new fn. So it's one function evaluation per step. But it is kind of funny. I agree that, right? So it's implicit but midpoint. So it's explicit but midpoint. And that makes it really nice and stable. You can reformulate this a little bit by taking this half step apart. So having the half function forces here. So you can pretend like your momenta are taking a half step. Then you compute positions with those half step velocities, and then you compute the next velocities. And this idea of a half step is also sometimes called leapfrog. So your velocities and your positions sort of are living on interleaving time lattices. What is nice about this, and why I'm showing is that it's very symmetric, right? I have this step and this step on both sides, and I've got my position step. This is why it's called the momentum relationship. The momentum part is cut in two, but it's also symmetric, right? So in this form, it's time reversible. If I did it backwards, I'd get the same thing. So if I care about time reversibility, this has it. And it should be time reversible because it was one of those midpoint algorithms, right? So that also gives us, so we have hopes for the stability, and it actually is very stable. And we have hopes for time reversibility. Very, very nice. How about all of the other nice stuff? Well, it has that too, depending on how you do things. So you noticed on the top here, it says symplectic algorithm integrators, because this is an example of that. Now, unless you've deeply studied statistical physics, you might not have come across the word symplectic. But it's a property of how nearby trajectories behave in the system. And it's one that's satisfied by Hamiltonian systems. And it's one of those things that guarantees you, for instance, that the canonical average, the microcanonical average, and a long time average are equal. So very important for statistical physics. But it also does some other things. It gives some sort of a stability. It sort of makes that if I have a clump of initial conditions and I look at them another time, they kind of take the same volume in your configuration space. Right? So there's no contraction, no expansion. A kind of stability in doing sort of sets of trajectories. So that symplectic thing comes from what's called Hamiltonian splitting methods. And it's kind of cute, and it sounds very fancy, but it's kind of cute. We can't solve a set of Lennard-Jones atoms exactly. Okay, we can't. But we can solve these sub-problems exactly. If there was no force, of course we could solve it exactly, right? Just streaming. And if there was no momentum, no positions, then I'd just be accelerating these particles. Kind of sounds funny, but that's what you're doing is you're replacing something you cannot solve, a Hamiltonian that you cannot solve, by a bunch of Hamiltonians that you can solve exactly. And then you write that H as a sum of those. You split up the evolution, so if U is the evolution, and then you compound them again. So it's a generic recipe that you can do to get higher order schemes, but it also shows, because each of the parts is a valid Hamiltonian or symplectic system, that if each of these parts satisfies your conservation laws that you're interested in, the whole does as well. So one of the things you can derive easily from that is each of these parts conserves linear momentum. And so your scheme does too. So if you split up your Hamiltonian in a way that conserves the conservation laws that you're interested in, you're good. Okay? And it's a Hamiltonian system. Actually, it's so cute that while we're making an approximation to the actual flow on configuration space, it turns out that you can write this as the evolution of another Hamiltonian that is very close to the original one by some order. So what you get is you're not actually simulating the Hamiltonian system that you thought you were simulating, but one that's very closely related. In that one, you're solving exactly, but you don't know what the Hamiltonian is, only in a series expansion. So you make h smaller, those two Hamiltonians come closer together again, right? So you're actually simulating a slightly different system up to an accuracy that you have in mind. But that new Hamiltonian can be shown to have all of the conservation laws that you put in. Good. So the Valais scheme is one and the simplest case of such an algorithm, and that's why it's so stable. That's why it does so well. Not because it's simple, not because we just took the midpoint, but because of all these sort of mathematical backgrounds where it's guaranteed that it does all of it. So we've got our stability, we've got our accuracy as best as we want, time reversal, symmetry, etc. Okay, so now Valais, great. There must be a library that does that, right? And so where are the molecular dynamics libraries? And the answer is they're nowhere. Well, that's not quite true. There are a few. There's one that I know that's sort of a framework. But the trouble is, since so much depends on how you compute the force, and that depends on what your force looks like, there's not much point in just a library. So you get applications. You get things like GROMACS and NAMD, which know force fields that are appropriate for atoms. LAMPS, which is a bit more generic, used much in material science, that have this stuff built in rather than being a library. They often come with some sort of scripting capabilities, but and they depend on what kind of forces they can do, how fast they are, how they can scale. A lot of them have been parallelized, so you don't have to do that. There is a framework called OpenMM, which I haven't played with much, but that's more of a framework. You're still writing a lot of the stuff yourself, but that's what's going. So much depends on the force fields that these are almost always either using canned applications or developing their own code. That's why it's important to know these techniques if you find yourself in a group that goes that way. Okay. Finally, then, let's go back from our biophysical friends and get to gravity. N-body gravity. So there's something special about this that you can see in molecular dynamics as well, but sometimes can avoid. And that's that gravity is a long-range interaction. This idea of coming up with a cutoff for your potential either means that your cutoff has to be so large that you might as well do the whole thing, or it just doesn't give you accurate results. And the latter is actually the case. So long-range interactions are sort of by definition when this cutoff idea does not work. Okay. Electrostatics is another example of this. Dipole interactions too. Quadrupole might be reasonably cut off, depending. But in any case, long-range interactions gravity cannot be avoided. So we're going to assume. So we're going to see what we can do about it nonetheless, because it would seem that the only thing we can do is have every particle interact with every other particle, every star with every star. So particle-particle methods, which are order n squared, seem unavoidable. But there's a few things we can do. I should warn you, they come at a cost. It's like magic. Some parts of accuracy, some conservation laws, you're going to lose some. But you can do things that go under names like Barnes-Hut, particle mesh, particle mesh, which is such a long word that it gets abbreviated to P3M, or Ewald sums, which are kind of related. I'm going to go over them sort of loosely so you know that these things exist and what happens, because if you're doing astrophysics simulations, you're likely going to use one of those. And this is actually just a start, I should take this. These are research projects, right? So none of this is the final solution of anything. Barnes-Hut, after the two people that obviously created it, kind of does this. It tries to clump particles together in cells. So here are some cells that you see. And if there's too many particles in the cell, essentially it divides it. So it's sort of a recursive algorithm to say when particles could be clumped together. And with clumped together, I mean you basically pretend like each box is one particle in its center. And then you can take those particles, those clumped together particles, and just compute those forces. So it leads to a reduction of how many forces. And the idea really is that for particles that are far away here, it doesn't really matter that this where the individual particles are here, just the collective effect of this mass distribution matters. So that's what you're trying to exploit. It leads to this thing called quad or octal trees, because you can divide in eighths, right, in 3 dimensions. You can go a little bit further. You don't have to just say, well, the mass in each box is just at the center. You can do a multiple expansion that will be more accurate. There's a whole, but it's kind of complicated. It works, I think. There are approximations you're making here. There's all kinds of details, but this is one of the ways you can sort of imagine going away from this. There's another way that is easier to understand for us, given what we've already discussed. And it starts with the particle mesh, which isn't very accurate, but we can fix that. And this does the following. It's kind of cute. We take our particles, these blue masses, and around them we put a rectangular grid, sort of out of the blue, or out of the black, yes. And we assign the points or the vertices on this mesh a part of this mass. So we distribute the mass onto this rectangular grid. Why do we do this? Because for a rectangular grid, it's actually fairly easy to compute what the gravitational potential is. And that's because the gravitational potential should be solved in this Poisson equation. So the Laplacian is equal to rho. But if rho lives on a regular lattice, we have a thing at our disposal called the fast Fourier transform. So this last week. And so we can solve this equation in Fourier space. The Laplacian becomes minus k squared, so it can solve for phi hat out of rho hat. So we basically Fourier transform this lattice density multiplied by something, get the gravitational potential. And then if we want the force, well, the force is the gradient of that potential. And so in the Fourier space, that's just multiplying by ik, or depending on your convention, minus ik. And so you've got the inverse of your force. And then all you have to do is an inverse f of t. You give the real force, you move the particles, you do the whole thing again and again. There's details on how you distribute the mass. There's details on how you compute the forces and interpolate that. But in principle, this would work and would give you an order n log n scaling just from the fast Fourier transform, which had that same. And n here's the number of grid points. Right? So the number of grid points shouldn't have to be much larger than the number of bodies, or you'll be in trouble. But the scaling is better. Okay. So that's the idea of this particle mesh, using the fast Fourier transform to solve the field, and then have the field generate the force again. That's very nice. But you can imagine that this can be very accurate for any interactions that are sort of close together, where this redistribution really matters. And so there's a patch for this. Particle-particle mesh. I mean, particle-particle interactions for nearby particles, and a particle mesh for the further away. So that's, I think, the best way to solve it. You can do, and so what you're trying to do here, and this is one thing that isn't quite clear right away, but we've seen if we do a Fourier transform, it basically turns any signal into a periodic signal. We saw the repetition of wave numbers. We saw that we have to shift things back to be. This is true here too. Unless you take drastic measures, your non-periodic system here has now become periodic. Essentially, this guy automatically lives here too. All right. So you've got periodicity here. That may or may not be bad. It's certainly not bad if we are imagining using periodic boundary conditions anyway, right? So actually, it gives us a way to deal with these periodic boundary conditions. And so we're essentially summing automatically over all these repeated indices by doing the fast Fourier transform. So so we have long-range forces. This would mean an infinite sum in their periodic boundary conditions. But this Fourier transform thing makes that into something that works. But we've put it on a lattice. Now there's ways where we can do this infinite summation not on a lattice, and that goes under Ewald sum. So I won't go into the details, but it's a way of avoiding the sort of the nearby inaccuracies. The only thing with Ewald is that it scales as n to the 3/2 rather than n log n, so it's a little bit slow. Whereas particle mesh still has the regular grid for the faraway charges or faraway masses, but the local stuff is better. So you can imagine that doing this right kind of gets involved, right? It probably depends on exactly what system you're solving. And so this is an active field, right? This is where research codes thrive, and people have to develop this themselves. You'll find established codes that do this. You won't find many libraries that do this for you. So all of this stuff, I guess, shows that when it comes down to it, at the end, you're probably writing some code. The fast Fourier transform is there for you. You're not coding that one in, right? You're using all the libraries that you need to, but you're still developing this. Okay, so that was an overview of using ODEs, but using them in a very physical way, or a very sort of realistic way for research. So here are some references. I like Frankel and Smith's book a lot, but then again, I did a lot of molecular simulations. Hockney and Eastwood are more towards the astrophysics part, but they agree on what they say, so that's good. And if you want to know more about this idea of sort of the mathematics behind it, how do these Hamiltonian splitting methods work, this is a very decent book explaining all the details about that. So if that's your inclination. Yeah. Questions? Okay. See you Thursday.
Am I trying to